date, go ahead and take out that proof in your class notes section that we started working on yesterday. We're going to do that before we go over the homework proof. And before we get to that, where we were proving that the bisector, the vertex angle of an isosceles triangle, is perpendicular to the base and bisects the base, before we get to that, I want to review some Clang statements with you. Statements that when you see them in the given, there should be an automatic association. You know when you see this, you're going to state that. For instance, if I were to see a midpoint in the given, Chris, what should I follow that thought up with? If I have a midpoint, then
equal sides. Equal halves.
Kind of equal segments, two equal line segments, right? So if I've got a line, and we'll just call it CH, and we're to have a midpoint, maybe pick a letter for me, Chris.
C.
C? Oh, I can't choose C, it's right there. R. If I were to pick a letter here, if R is the midpoint, then I know that
C and H are equal.
Help in Genesis?
CR is equal to HR.
There we go. I know that CR equals HR. If I'm told in the given R is the midpoint of CH, clang, CR equals HR. Those two segments have to be equal to each other. Another clang statement we might see is the word perpendicular. Kendall, if I ever see perpendicular in my given, clang, I have right angles. So if I were given that ZR is perpendicular to CH, I'm going to call these angles 1 and 2. If I see ZR perpendicular to CH, Kendall, clang, I state
angle 1 equals angle 2.
No. Ethan? If ZR is perpendicular to CH, then that means what's the Clang response to perpendicular, class? If I have a perpendicular, I have right angles. Okay, so that means I should state that angle 1 and angle 2 are right angles. You know, in this case, since I had two of them, I suppose if it were just this, then I just say angle 1 is a right angle, or angle R is a right angle at that point. Yeah, you got a perpendicular, clang, you got right angles. If I'm told that I've got an angle bisector, so suppose I've got an angle here, G and H, and I've got a line NV, that, and I'm told NV bisects angle G and H. Then Audrey, what's the Clang response to an angle bisector?
You have to equal angles.
Clang, two equal angles. So if I call these angles 1 and 3, what would be my Clang response to the angle bisector? Angle 1 equals angle 3. I would state that based on the definition of an angle bisector. And yesterday I gave you a new Clang statement. And it was this, that if I have a triangle, and in that triangle, this is a bad triangle. If in triangle BAD, I'm told that, side AD equals side BD. Anytime I've got a triangle and two sides are equal, Clang, who remembers from yesterday the Clang response? Two equal sides.
Isn't it two equal sides equal respectively to the two other sides of the other triangle?
No, that's pretty fine. That would require two triangles, Ethan.
The opposite sides is equal, or opposite angles?
The opposite angles are equal. If in a triangle two sides are equal, clang, the opposite angles are equal. Angle A equals angle B. This is now a clang response. That's 4 clang statements. Midpoint clang, 2 equal segments. Perpendicular clang, right angles. Angle bisector clang, 2 equal angles. Triangle with 2 equal sides, clang, 2 equal angles. These are responses we've got to have just automatic as soon as we see them in the given. So taking a look then at the proof that we set up and did not actually start yesterday in your class notes. If you haven't already, go and get your first statement and first reason down. I don't know if we got that far or not. But we had a triangle that was given to us as being isosceles. And what did we name the triangle yesterday, Chris?
JRQ.
JRQ. And we had the perpendicular, no, we had a bisector. We bisected the vertex angle. And we called this point down here, class, T. Okay? And so we said, given that the triangle, first of all, was isosceles, right? Isosceles triangle JRQ with vertex angle Q. Yes, I think we did get the first statement and first reason down, didn't we? All right, so isosceles triangle JRQ with vertex angle Q. And I said that QT bisects angle Q. Was that the whole given, or was there something else we had in the given? That's the whole given. And then we said we were going to try to prove this, that if you have an isosceles triangle with the vertex angle being bisected, that bisector of the vertex angle, number one, will also bisect the base. So we needed to prove that QT bisects JR. We also wanted to prove that the bisector of the angle is perpendicular to the base, so that QT is perpendicular to JR. So far, so good. This is what we had in our proof when we left off yesterday. All right, so we've got two columns, we've got statements, and we've got reasons, because we never make a statement unless we got a really good reason. And for sake of time, I'm just going to draw an arrow up there because you already took time to write that. All right, number 2. Did we get a second statement down yet, or we literally got as far as the first statement? Okay. All right, so, clang! I've got 2 clangs in here. The first clang I see is the obvious clang bisects. Again, what does it mean, Chris, when an angle is being bisected? What does it mean for an angle to be bisected? What is an angle bisector? Definition word for word.
Angle in half.
No, divides an angle into 2 equal halves or into 2 equal angles. So, listen again. What is an angle bisector? It's that which divides an angle into 2 equal angles. The last 3 words of the definition are the key. 2 equal angles. Okay, so Chris, what 2 equal angles are there? QJT and QTR. These 2 angles are equal? Because of this bisector? QRT. So because this angle right here, Chris, is being bisected, those 2 angles are equal?
Yes. No.
So if I bisect Genesis, I'll divide Kendall into 2 equal parts?
No, it's 1 and 2 at the top of Q.
There we go. Angle JQT and angle RQT, or we could call these angles 1 and 2. By the way, quick strategy tip here. Quick strategy tip. Let me refresh my picture now that I messed it up. Whenever you're given a picture and you see that at a particular point there are multiple angles. For instance, notice in drawing this picture, there are 2 angles at Q and 2 angles at T. At J, at this point, there's only 1 angle. At R, there's only 1 angle, but there's 2 different angles here and 2 different angles here. Just number everything. Right up front, before we even start the proof, let's just number 1, 2, 3, 5. Just get all the numbers up there, so that way we can, okay, I'll take it easy on her. 4. Anyway, but number the angles first, because it makes it so much easier to see. So Chris, coming back to you now that we've numbered the angles, QT bisects angle Q. What must be true? Angle 1 must equal angle 2. And how do we know those 2 angles have to be equal?
Angle bisector.
Good, based on the definition of an angle bisector. It's that which divides an angle into 2 equal parts or 2 equal angles. Therefore, those are the 2 equal angles. All right, there's another clang, and it's not one of our major clangs that I've drilled, but it's this word isosceles. What does it mean for a triangle to be isosceles, Ethan?
At least 2 equal sides.
It must have at least 2 equal sides. Generally, we'll assume 2, right? Because if we had 3, we would have said equilateral. So for our purpose, let's assume 2. And remember, based on terminology, we said the 2 equal sides will be called the legs. The non-equal side will be the base. Hypotenuse is in a right triangle. And we said that the angle formed by the legs is called the vertex angle. Therefore, if this is the vertex angle, these must be the legs and this must be the base. So if these must be the legs, then which 2 sides in the isosceles triangle must be equal?
QJ and QR.
QJ and QR must be equal based on the definition of an isosceles triangle. QJ equals QR, definition of isosceles triangle. But I just created another claim statement by saying that in this triangle, two sides are equal. Clang, Audrey. The new claim we created yesterday. Good. If anytime you have a triangle and two sides are equal, the angles opposite the equal sides, the angles across from the equal sides have to be equal. So Audrey, if indeed, and we proved they must be, QR and JR are equal, what angles then must be equal in this triangle? In this triangle, this line is sort of blurring your vision here, but the triangle is still QJR. So what side of this triangle is, or what angle of this triangle is across from QJ? Angle R. And what angle is across from QR? Angle J. Now again, you could look at it, oh, there's 4, there's 3. Careful, those aren't in the big triangle, right? Those are in the little divided triangles by this big bisector. But angle J and angle R must be equal. Because in a triangle, angles opposite equal sides are equal. In a triangle, angles opposite equal sides are equal. That's a clang statement. You have equal sides, clang, there's equal angles. Just like you got a bisector, clang, there's two equal angles being formed by it. You have an isosceles triangle. Yeah, clang, you got two equal sides based on the definition. All right, so that's clang. And the reason I call them clang is because you don't even think, you just do. You just react, you just respond. We haven't even done our analysis yet. It's okay, clang comes before analysis because it just leaps off the page and grabs you. You just got to put it down. Now, let's think about what we're trying to prove. I'm trying to prove that QT bisects JR. What does it mean, Genesis, if QT bisects JR? It must divide JR into two equal parts. What would be the two equal parts if QT is the bisector? JT and RT. So class, you understand that if we could say that JT equals RT, then QT must bisect JR, correct? If this is true, then that must be true. So here's the question. How can I prove that these two segments right there are equal to each other? Well, if T were the midpoint, but it doesn't say T's the midpoint. But there's another way to prove that two line segments are equal to each other if they are in two different triangles. Particularly if there were a way to show that these two triangles were, class, congruent. Good, Chris, because if the triangles were congruent, then wouldn't these two sides have to be equal by CPCTE, right? Yeah, of course they would. So the question is now, can I get these two triangles? Can I get triangle JTQ congruent to triangle, let's see, how should I letter this one if I call this JTQ? Chris? RTQ. R clearly corresponds to J, and Q corresponds to the other part of Q, so T would have to correspond with T, so RTQ. If these two triangles were congruent, class, then these two lines would have to be equal by CPCTE, and so then QT must bisect JR. Do you see the analysis, the progression here? I want this, but to get this, I would need this. To get this, I would need this, okay? We're trying to prove congruent triangles. I've got two main ways to do that. What are the two main ways, Kendall, to prove triangles congruent? All right, so now, Ethan, let's look at the picture. Let's see, what do I already have? What sides, angles do I already know are equal in these two triangles?
Angles 1 and 2.
Angles 1 and 2 are a couple of angles, good.
And then side QJ and KR.
QJ and QR.
QR, yeah.
All right, so there's a couple of sides.
And then angle J equals angle R.
Angle J and angle R. So class, I do have what already? Angle, side, angle. And this is why I love to get the claim statements down. It doesn't always take care of all the parts, but a lot of times you can get some of these sides or angles just through claim statements. I've got angle, side, angles, so class, what must be true about the triangles? They have to be congruent. Number 5. I know that triangle QT or JTQ is congruent to triangle RTQ by angle, side, angle. By the way, it's not in the given, but there is another claim statement. I've got 2 triangles that share a side. I could have said QT equals QT by identity. And then I could have had side angle, side if I wanted it, right? I didn't go that route, but I could have, okay? So we've got the congruent triangles, and because the triangles are congruent, class, that means that JT and RT are equal. Because they are corresponding parts of congruent triangles. So RT equals JT by CPCTE. And because JT and RT are equal, that means that QT has then divided this line into 2 equal parts. And if one line divides another line into 2 equal parts, then that line must be the bisector of the line, right? Perpendicular doesn't mean divided into 2 equal parts, because you can have a perpendicular that doesn't divide into equal parts. But a bisector always does. Therefore, number 7, because we have 2 equal segments formed by the line QT, QT does bisect RJ. I wrote the R first by accident. QT bisects RJ. How do I know? Well, that's based on the definition of a bisector. So item 1, taken care of. We now know that in any isosceles triangle, bisecting the vertex angle will bisect the base. But I'm not done. I want to prove that QT is going to be perpendicular. Well, what does it mean to be perpendicular, Chris? To make right angles. So, Chris, these 2 lines will indeed be perpendicular if which angles are right angles? 3 and 4. So you understand, class, that if angle 3 and angle 4 are right angles, then QT must be perpendicular. This is my analysis. How could I show QT is perpendicular? If I can show that 3 and 4 are right angles. How to get 3 and 4 to be right angles? Well, the secret here lies in the definition of what a right angle is.
Isn't right angle 2 angles that form a straight angle?
No, supplementary angles are 2 angles that form a straight angle. Look it up in your notes. This is one of those definitions most students struggle with anyway. So go ahead and look it up in your notes. Let's see, what is a right angle?
What 2 straight lines to form adjacent equal angles?
The angles formed when 2 straight lines meet to form equal adjacent angles. Class, do I have 2 straight lines that form angles 3 and 4?
Yeah.
Yes, there are 2 straight lines. Do they form adjacent angles 3 and 4? Are they adjacent?
Yeah.
Yes, they must be because they have a common vertex and a common side between them. So 3 and 4 are adjacent. Are they equal?
They have to.
Why?
Because it
It's
says
all right
equal
angles.
adjacent angles by the definition.
Well, no. If they're equal adjacent angles, then we have right angles. Or if I knew they were right angles, I'd know they were equal. But it's like circular logic. How do I know they're right angles? Well, because they're equal adjacent angles. How do I know they're equal? Because they're right angles, they're equal adjacent angles. I don't know that yet. How do I know 3 and 4 are equal? Or are they?
They have to because JR and QT in 2 straight lines form and make right angles.
I don't know that they make right angles. I'm trying to prove that they make right angles. I don't know that they make right angles
Is
yet.
that the definition of perpendicular or 2?
I don't know that they're perpendicular. I'm trying to prove they're perpendicular.
Oh, wow.
It's like, for instance, saying, I want to prove that Donald Trump is a liar. Well, if he tells lies, so I know he's a liar. Well, how do you know he's a liar? Because he's a liar! And actually, that sounds about like the argument people make. Anyway, though he is a sinner, so I'm sure he tells something. He does tell a whopper or 2 every now and then. But anyway,
All right angles are equal.
I don't know that they're right angles, though. You're saying, well, they must be equal because they're right angles. No, I don't know that they're right angles. I want to prove that they're right angles.
Prove that it's congruent.
What's congruent?
The two different separate triangles.
Oh, the 2 triangles are congruent. And these angles are corresponding parts of congruent triangles. So angle 3 and angle 4, put that in number 6, they are equal by CPCTE. So now that we know that, yes, they are equal adjacent angles formed when two straight lines intersect, by definition, number 8, angle 3 and angle 4 are right angles. Angle 3 and angle 4 are indeed right angles based on the definition of what a right angle is, the definition of a right angle. And since 3 and 4 are right angles, that means that these two lines then, class, have to be perpendicular. Number 9, we're done. QT is perpendicular to JR. How do I know that?
We just proved it.
How? What's my reason? How do I know they're perpendicular?
ASA? No.
The ASA proves triangles congruent.
CPCT.
Well, that just proves corresponding parts are equal. It doesn't prove anything about perpendicular. How do I know QT and JR are perpendicular? What does number 8 say, class?
3 and 4 are right angles.
Right angles, okay? So why does that mean perpendicular?
Because perpendiculars form to make right angles.
Ah, that's the,
Definition of perpendicular.
there we go, definition of perpendicular lines. How do I know they're perpendicular? Because we have right angles. And perpendicular lines make right angles. That's the definition of perpendicular lines. Finish out that perpendicular symbol.
Be sick more often, I'm smart.
And there we go. Questions on this proof now. So that's interesting. No matter what isosceles triangle you draw, doesn't matter even how you draw it, any isosceles triangle, if you bisect the vertex angle, meaning the angle formed by the legs, this line will always be perpendicular to the baseline and will bisect the baseline. Any isosceles triangle, we just proved that. Yes, sir.
So on number 7, on the reasons you put def of bisector.
Definition of a bisector, that which divides into two equal parts.
Right. So what's the difference between that, the definition of that, and angle bisectors?
An angle bisector specifically divides an angle into two equal angles, but you could say still just definition of bisector because it divides into two equal parts. They just happen to be angles.
I didn't know if there were like 2 different definitions.
Not really. A bisector is a general term that any time you divide into two equal parts, you have a bisector. It could be a guillotine blade. I mean, heaven forbid. Though usually they didn't sever into equal parts, but it could have. Typically, but angle bisector is just a more specific definition.
How do you see all of this? Like, it would take me like an hour and a half to figure this out.
But this is why I'm coaching you through this. I'm helping you to see. So hopefully, as I'm explaining, you're like, okay, I kind of see that. This is why we do a lot of proofs. In fact, this whole hour is nothing but proofs. Lots and lots of proofs today. No new material, just proofs, including your homework proof. Take that out if you would, please. Go and take out your homework proof. And let's see how you did filling in the blanks on handout 6 for homework last night. See how you did filling in the blanks on handout 6 last night. There's a pattern in this proof that I want you to see. This is the first time you've encountered this pattern. We started with an isosceles triangle, and the isosceles triangle was ABC, and it was isosceles such that AC and BC were the equal sides or the legs. The proof then said that AB was extended through A to some point D, and was extended through B to some point E. But these 2 points were chosen such that the 2 segments, AD and BE, were equal to each other. I wanted you to prove, first of all, that the angles formed out here, 1 and 2, had to be equal. I then wanted you to prove that if you joined these points D and E up to C, that those 2 triangles formed would have to be congruent to each other. Hold up handout 6 so that I can see that it is completed to the best of your ability. All right, excellent. Let's go and take a look here. Course number 1, your first statement, isosceles triangle ABC with AC equal to BC. AB is extended through A to D and through B to E so that AD equals B. Reason, class, given. Number 2 is your Klang statement. The reason I said is that angles opposite equal sides in an isosceles triangle are equal. Genesis, which triangle is isosceles?
ACB.
ACB. This is given as the isosceles triangle. and these are given as the equal sides. So if angles opposite equal sides in a triangle are equal, which angles are equal?
Angle
1 and 2 aren't in the triangle. 1 and 2 are outside, they're exterior to the
1 and 2.
triangle. The little angle A and the little angle B. So for number 2, you should have written angle A equals angle B. How many recognize that these two angles had to be equal because they were opposite equal sides in the isosceles triangle? Questions on that? Yes, sir.
I put angle 1 equals angle 2.
As I just said in Genesis, those are exterior to the triangle. They're not in the triangle. Angles opposite equal sides in a triangle are equal. They're not in the triangle. Does that make sense now?
Kind of.
All right, number 3. I then said this, that angle 1 plus angle A is a straight angle. And then angle B plus angle 2 is a straight angle. And I went ahead and gave you the reason. I said it's because, in formal statement 10, the sum of all the angles about a point on one side of a straight line equals a straight angle. The sum of all the angles, all both of them, about a point on one side of a straight line equals a straight angle. But then I said that if you were to take angle 1 plus angle A, it would equal angle 2 plus angle B, because all straight angles are equal. Questions on statements 3 and 4 and the reasons for them. Does it make sense? It does not make sense, Ethan.
Oh, it does.
It does make sense, okay? Does it make sense on 3 and 4? Now then, in statement 5, I said if you subtract equals from equals, the remainders will be equal. In this statement that you had for number 4, which two things do we already know to be equal, Audrey? A and B. We stated in number 2 that A and B were equal. So since we already know that they're equal, we could subtract A and B from what we had in statement 4. And that would leave us with what statement for number 5, Audrey? Angle 1 equals angle 2. How many had that statement for number 5? All right, do you see the progression here? We know that A and B are equal because they're across from equal sides in an isosceles triangle. We also know that together 1 and A make a straight angle, 2 and B make a straight angle, which means that 1 and A and 2 and B together, their sums must be equal because all straight angles are equal. But since A and B are already equal, they could be subtracted away, leaving me with angle 1 equals angle 2. And that's where we end up with number 5. Now, that takes care of the first thing we wanted to prove. We wanted to prove angle 1 equals angle 2. That's done. The next thing we wanted to prove was that triangle DAC is congruent to triangle EBC. Well, what are ways we would use to prove triangles congruent, Chris?
ASA, SAS.
And if they were right triangles, like angle, we don't have any indicator of right triangles. Well, looking at these two triangles on the sides here, Chris, what things, sides, angles, do we already know to be equal?
A and B.
A and B?
We know angles A and B are equal.
Which angle? There's 3 angles at A. Which angle?
And the middle triangle. Like it's
Oh, these little a and little b. Okay, those aren't in these triangles. We're looking at the side triangles right now.
1
Right.
and 2.
Angle 1 and angle 2. We just said they're equal. So that gives me a pair of angles.
It says AC and BC are also equal.
Right, they were given as being equal, so there's a pair of sides.
And then
What else were we do we know to be equal? Ethan, help him.
DA and BE.
DA and BE were given to us as being equal as well. Ah, so class, what do we have right now?
Side and side.
Side angle side. And that's how we'll prove number 6, that triangle DAC is congruent to triangle EBC. I'm not hating on DAC. Number 6 is using side angle side. He just got it. Anyway, triangle DAC is congruent to triangle EBC. Ethan, slow. My side angle side. Questions on this proof? Did anyone get side angle side for the reason the triangles were congruent? Anyone fill in all 1, 2, 3, 4, 5, 6 blanks correctly? Got all 6 blanks right. Okay, pretty good. Those who did not, does it make sense now?
Could we do another one as proof angles?
What?
Could we do another one like that?
We'll do several more. In fact, go ahead and turn your handout over. Just use the back side of the handout now. And I want you to draw a nice tall isosceles triangle. So just leave as quietly as you can. All right, ready to resume video. All right, go ahead and draw a nice tall isosceles triangle on your paper. And call it ABC. A nice tall isosceles triangle on your paper and call it ABC. Draw it such that AC and BC are 2 equal segments, 2 equal sides. Right there, you should already be thinking of a clang, but you can't put it down yet because we haven't set up our 2 columns. All right, I also want you now to come down a certain distance from C. Whatever distance you feel is good. Pick a point coming down from C, call it D. I want you to come down that same distance from C and mark it off on the other side, E. Now, if we were doing it perfectly, we'd use a compass to make sure these were exactly equal. We don't really care that much. But we're going to notate that CD and CE are equal segments here. I also want you to locate approximately the midpoint of AB. We'll say it's the real midpoint, call it M. We don't know what it exactly is, but we could, right? We could do construction 1, we could find the midpoint. There is one point anyway. We're just going to say we found it, okay? So go ahead and mark the midpoint now of AB, call it M. Here's what we're given. We're given everything we just drew. We're given isosceles triangle ABC with AC equal to BC. We're given that DC and EC are equal. We're given that DC and EC are equal. Marked off points on AC and BC. We're also given that M is the midpoint of AB, the base. Move this out of your way, Genesis, so you can see a little bit better. Now, real quick, there's a notation on here. Remember I put the tick marks to show that AC and BC were equal? These tick marks almost make it look like AD and BE are equal. I don't want to confuse anybody by just indicating that they're equal. So I'm going to go and do this. I put a tick mark here, and like this, and a tick mark here. So we know that AC and BC are the big lines that are equal, just so it's really clear. All right, what do we want to prove? Well, we want to prove that if I give you any isosceles triangle, we drew it tall, it could work with a shorter one, no matter how far down you come from C, as long as you mark that exact same distance, if you then connected these 2 points to the midpoint of the base, then you would form line segments that are equal. I want to prove that if you draw lines from these 2 points to the midpoint, that those 2 lines must be equal. Let's prove that DM equals EM. Let's prove that DM equals EM. Once you have that down 2 columns, statements, reasons. By the way, watch. 1, 2, 3, 4, 5, 6, 7. I don't know if I need those angles or not, but I like to be in the habit of, if there's multiple angles at a point, number them. I don't even want to have to think about 3 letters because I'm a mathematician and mathematicians are lazy. Now, A only has 1 angle, B only has 1 angle, C only has 1 angle. I'm just going to number the rest of them. I don't know if I need them or not. I don't care if I need them or not. I'm just going to label them. All right, now, first statement, first reason. That's a strategy tip, by the way. Let's see here. Clang and clang. I got 2 clangs. Volunteer for one of the clangs. Ethan.
Isosceles triangle.
Well, but usually we'd use that to get 2 equal sides. I actually put the 2 equal sides right there in the given. So no, someone else with another clang. Kendall. Midpoint. That's a great clangy word. What do I write in my proof because I have a midpoint?
M is the midpoint.
Yeah, I already know M is the midpoint. What do I put in my proof? What must be true because M is the midpoint?
AM equals BM.
AM equals BM. Reason? definition of a midpoint. Good, there's one clang. There's another clang in here. Volunteer for the other clang. Got a triangle with two equal sides. Clang. Audrey? Yeah, if you got two equal sides, you can have two equal angles across from them. Now again, Audrey, this is where we got to tune this out. The two sides are equal in the big triangle, so tune out all the mess in the middle for a minute. What angles in the big triangle are across from BC and AC?
B and A.
I asked Audrey. Audrey's voice just got deeper.
Yeah.
Good job, Audrey. Angle A and angle B, right? A across from BC and B across from AC. So number 3, I know that angle A equals angle B because angles opposite equal sides in a triangle are equal. Or I guess I usually say in a triangle, angles opposite equal sides are equal. But anyway, whatever. Says the same thing. Doesn't have to be word for word per se. Angles opposite equal sides in a triangle are equal. I suppose if Audrey was like, well, I got a triangle and two sides are equal, so I know the angles that are across from those equal sides, they've got to be equal. If she wrote that, I would take it. Because it's true. It's not a lazy man's version of true, but it's true, isn't it? If I got a triangle, and in that triangle I know that two sides are equal to each other, then the angles that are across from those equal sides have to be equal to each other also.
Write all that.
Good. I'm too lazy to write all that, but you're fine if you write it. So again, word for word doesn't per se matter here as much. All right, so I think that's all the clang I've got. Now let's look at what we're trying to prove. I'm trying to prove that these two lines right there are equal to each other. How can I prove that two line segments are equal to each other? Well, what's the usual way we get lines equal around here, class? Congruent triangles followed by CPCTE, right? Okay, so if we stay with the process we seem to use an awful lot for now, what triangles would we want congruent genesis so that DM and EM could be equal? ADM and BEM, right? Do we all see that if we could get triangle ADM congruent to triangle BEM, if these two triangles were congruent down here, then the lines would have to be equal by CPCT. Everyone good with that? That's analysis. What do I need to make this happen? What do I need to get that? I need two congruent triangles right here. Now, when I think of congruent triangles, I think of two main ways to get congruent triangles, Kendall. And every time I think of that, I think, well, what do I already know? In those two triangles, are there any sides, any angles that I already got this? Ethan?
Angle A and angle B are
Okay,
equal.
there's a pair of angles equal.
And side AM and side BM.
Side AM and side BM. Okay, anything else?
Right now it's all.
Nope, that's all we have so far. So I've got angle side. So I've either got this angle side or this angle side. So either I need another angle or I need another side. Make sense? Let's think. If I wanted to go angle side angle, I've got angles, sides. What angles would have to be equal, class?
3 and 5.
3 and 5. Is there a good way to get 3 and 5 equal to each other? I'm glad you didn't say, ooh, they're vertical angles, Mr. Nadasky. Are they vertical angles, class? How many lines form vertical angles? 2. How many lines do I have forming angles 3 and 5? 3. I've got AB, ME, and MD. So no, 3 and 5 are not vertical angles. I can't think of a good way to get those things equal to each other. I mean, it's CPCTE, but then it already have the triangles congruent, right? So let's cross angle, side angle off the list. All right? What if I wanted side angle side? I've got side, angle. What sides would have to be equal, class? AD and B. All right? Do I already know they're equal? No, otherwise we would have said so. But I do know this. I know that these whole big sides here are equal.
Mm-hmm.
And I know that these little pieces got cut off and they're equal.
Subtraction axiom?
So the subtraction axiom is what we should be thinking here, right? Because if we were to subtract equal quantities from equal quantities, the remainders would have to be equal, right? So does it not make sense that we want ADBE equal? And if they are, and we're going to get them that way, I've got side angle side, I've got congruent triangles, therefore DM and EM are equal. Does it make sense? This is called analysis. You put your options on the table, you think through your options, you see which one works. We thought about angle side angle. We decided we didn't know how to get it. We thought about side angle side. We're like, I bet I could do that one. That's analysis. So, let's get ADBE equal. It starts this way though. Listen to me carefully. I know that the whole lines are equal. I also know that these little parts are equal. But I want these other parts to be equal. You should be thinking something with the words I've emphasized. Whole is equal to the sum of its parts. And that's where you actually have to start. We can't go straight to the subtraction axiom yet. We're going to start by simply stating that the whole side AC is equal to AD plus DC. Similarly, the whole side BC is equal Genesis to there we go, is equal to BE plus EC. I know that's true because the whole is equal to the sum of all its parts. Anytime you're dealing with wholes and parts, you got to start this way, okay? I know you're thinking subtraction axiom, right, but we got to get there first. Now, here's the deal. Since AC and BC are equal, and AC is that, and BC is that, I can take this, plug it in. I can take this, plug it in. That's called substitution. So the next thing we're going to do is we're going to do a substitution. Since AC and BC are equal, then AD plus DC must equal BE plus EC because of the substitution axiom. And now we're finally ready for what we wanted to do all along, and that's that subtraction axiom. I now have two equals from which I can subtract away equals. If I subtract these two equals from those equals, what's left? AD equals B. Take DC off, take EC off, and you're left with AD equals BE. Subtraction axiom. And now, I broke my chalk. I mean, now we have side, angle, side. So my triangles class are congruent. Number 7, triangle ADM is congruent to triangle BEM by SAS, side angle side. All right. Any questions on this proof? Good, good. There should be a question. We're not done yet. It didn't say to prove that. It said to prove that. We haven't done it. Don't stop a proof before you're finished. No, for heaven's sakes. I've seen this too. Students keep going with the proof after they've already proven what they're supposed to prove. I'm like, why do you keep going? You're done. Anyway, yeah, don't stop till you're finished. We haven't proven that DM equals EM yet. Oh, how do we get that? CBCT, that's the whole reason we got the triangles congruent in the first place, was so that DM could equal EM by CPCTE. Those two lines are corresponding parts of what are now proven to be congruent triangles, so they are equal to each other. Questions on this proof? I want you to note these 3 steps. You remember that paper the other day where I had you point out 3 steps that were a little cluster? It was whole equal sum of parts, addition axiom, substitution axiom. That's where you know 2 pieces are equal and you want to get the wholes equal. Here, I knew the wholes were equal and one of the parts equal, I wanted the other parts equal. This little 3-step process is worth putting a star on and saving this paper. Put a little star there and make sure you save this paper. You're going to want it for reference. The next time you want to do a subtraction, this is the way to go about it. Always start whole equals sum of parts. We can substitute the parts in for the wholes and subtract away the parts we know to be equal. All right, new sheet of paper. We'll set up a proof at least. And once again, it seems like every day we get to 5 minutes left, which is not enough time to do a whole proof, but I guess we can try to speed through a proof here. I want you to draw another isosceles triangle. Notice a theme going on here. Let's see, Ethan, do we want to draw tall or short?
Short.
Let's draw a short, squatty isosceles triangle. Not that short always implies squatty, but in the case of an isosceles triangle, if it's short, it must be squatty or just small to begin with. All right, and let's call our triangle ETJ.
Maybe
Jet.
it's tall.
May the New York football team ever struggle. All right. And then what I want you to do is on the end of E, I want you to draw a short little perpendicular. And on the end of T, I want you to draw another short little perpendicular that's the same height as the other one, to the best of your ability. Of course, with a compass, we could measure, make it perfect. We don't care that much. And let's call these points K and M. I then want you to connect J to K. No, really, I want you to do it. And I want you to connect M to J. Genesis shakes her head at me. JK. All right. Anyway, all right. So here's what we are given. Here's what we are given. We're given an isosceles triangle, JET, with JE equal to JT. Isosceles triangle jet with jet equal to jit. We know that K is perpendicular to et, and we know that mut is perpendicular to et. So you got a couple perpendiculars. We also know that K and mut are equal to each other. Because that's what we drew. Basically, the given is just an illustration of all the stuff that was drawn in the sketch. Or you could say the sketch is an illustration of all the stuff that was in the given. Here's what I want us to prove. And tell you what, I'll let you try this for extra credit tonight. Again, I know it's a long shot, but I'll tell you what, if you're really close, close enough to please me, I'll give you a point just for being really close. If you nail it, I'll make it worth double. I'll give you 2 extra credit points on your next test. Okay, so, and if you don't get it, it's okay, you can still learn from it. If you don't do it at all, I'll be highly disappointed in you, but I won't be angry, and I won't give you homework offense. We just want to prove that the 2 little triangles here are congruent. Prove that triangle KEJ is congruent to triangle, let's see, K would correspond to M, E would correspond to T, and J to J. And since we don't have time to do it now, go and give it a shot for extra credit. See how you do. And we'll go over it tomorrow. I will suggest that you number 1, 2, 3, 4. You're going to want to refer to those angles in the course of the proof. You should not need these angles up here. So I'll give you that little hint. Don't bother with those angles up there. Just focus on using some angles down here. All right, well there you go. We'll give it a shot tomorrow, see how you did, or give it a shot tonight. Tomorrow we'll see how you did, and have a wonderful rest of your day.